This is a video explaining how to use right triangle trigonometry for finding the sides and angles in a triangle. So to start off, we're going to look at what exactly do sine, cosine, tangent, cosecant, secant, and cotangent mean? What are they in a right triangle? Well, let's take a look at this right triangle. So I've drawn a right triangle and I've given it one acute angle of 35 degrees. Don't know what the side measurements are. And using my calculator set in degree mode, I went ahead and got the answers to sine, cosine, tangent, cosecant, secant, and cotangent. I get 6 very strange decimals. So what do those decimals even mean? Well, remember, we did this in the scale factor review. The sine of 35 is just the scale factor that exists when I divide the A side by the C side in any right triangle that has a 35-degree angle. That's what it does. We looked at that there are 6 different ways we could divide these 3 sides to find the scale factors. So if I'm looking at the scale factor from A to C, that gives me the sine. And we know from similar triangles that in any triangle like this one with the same set of angles, it'll be the same scale factor between pairs of sides. So that's what the sine represents. It's one scale factor. So now, if I look at this, if this side is 10, this side would have to be 5.736, so that when I divided them, I got that. If this side were 6, this side would have to be this strange 10 point something, so that it would divide out. If this side were 1.472 and this side were 2, it would divide out. So all of these are similar triangles. That 35-degree angle fixes what this ratio should be because of how much that 35-degree angle opens. It's like it opens this far. And if I go to a smaller triangle, it opens that far. And if I go to a bigger triangle, it opens that far. So that's what that 35-degree angle is doing. So when we look at this, if I want to find the scale factor between 2 sides, I would have to divide them. And to find the scale factor between 2 different sides of different shapes, you divide them. So I'm really doing this A altitude, C hypotenuse side, and I'm getting 0.5736. So if I needed to solve for A, or if I wanted to write this as an equation, then A is about 0.5736 times C. That's the scale factor. That if I want to turn C into A, I'm doing just over half of C. So there are the 6 different ratios, and there they are. So I could compare A to C, B to C, A to B, or I could flip each one of those, C to A, C to B, and B to A. So 6 different ways I could calculate scale factors, depending on who I want to start with and who I want to end with. Now, the reason we have to put an angle, and the angle is so important, is that tells me the ratios. That gives me that perspective. It's a reference that tells me, okay, if this is the angle, here's how much it's opening. And so then we know which one of these comparisons we're doing. That's why there are the 6 trig ratios. This angle fixes the perspective, and we know that the ratios for every angle are also fixed. We saw that in our trig table. So there are the 6. Calculating 6 different ways of looking at scale factors gives us the 6 different trig ratios. Now, if we have a scale factor, we can find the length of a missing side. That's something we've done before, where you're given the scale factor and you're told what's the length of the missing side. So then what good is trig in right triangle form? Why do we need it? Well, the number one thing that trig makes things easier for us is when we need to find the length of a side. So let's say I gave you this right triangle. It has that 35-degree angle. We're going to use that one again. And the hypotenuse is 13 inches. And I want to know the height of the triangle. Maybe I want to look at finding the area of this triangle, and so I need the height to be able to do that. Well, we're given the side length of 13. We need a side length of x. We know there's a 35-degree angle, and we know that that 35-degree angle has a set of scale factors between its sides. All we got to do is figure out which scale factor we're dealing with here and just pull up the number. So there it is again, a quick reminder. Which scale factor do we need to pick? Which ratio? Well, we had the green and the orange side, so that gives us two options. So we have the hypotenuse, we have the height, and there are two ways we could do it. Now, if I do 13 over x, I'm dealing with cosecant. If I do x over 13, I'm dealing with sine. And, well, let's just face it, there's a sine button on a calculator. In a trig table, sine is one of the listed options. So I think I'm going to go with the ratio that's easier to work with. So I'm going to use the sine. I know the sine. The sine of 35 is a fixed value for every right triangle that has that 35-degree angle in it. This is a constant. It is set in stone. So I know that if I compare the x and the 13 side, that is what the ratio has to be. Well, then if I multiply by 13, I get that x is about 7.4568, or about 7.5 inches. So using my trig, I was able to find the height of the triangle. Let's look at another example. So here is a triangle. I have x and 12 and a 20-degree angle. So maybe I really do want the area of the triangle. Here's my height. I need to know my base. Well, there are two ways I could look at it. I could compare x to 12, or I could compare 12 to x. X to 12 is the comparison that makes the cotangent. 12 to x makes the tangent. Again, since I have a tangent button on my calculator, I think that's going to be the winner. So 12 over x is the tangent of 20. That means 12 is x times the tangent of 20. Remember, tangent 20 is just a number, and right now I just don't feel like writing that number down. So then I come over here, and I'm going to have to divide by that number to isolate x. So it's going to be 12 divided by whatever tangent of 20 is. All right, to the calculator. So I type in 12 divided by tangent 20. Of course, make sure we're in degree mode. And that's what I get. So if I round to the nearest tenth, that means x is about 33.0. The 6 rounds that to 10, and that's why we put the 0. We're showing that we rounded to the tenths place even though it rounded up to 33. All right, how about you try this triangle, just this one right here. Go ahead and see if you can find the value of x using a trig ratio. Pause the video and do that now. All right, here we go. Let's see how you did. So I had two ways I could have compared x and 10. One of them would have been the secant. The other was the cosine. Cosine's on my calculator. So I set up my ratio for cosine. I multiplied by x, divided by cosine 65, went over to my calculator, did the math, and rounded to the tenths place. So now let's do the number 2 way of what is good about trig. Trig, and this is maybe even better than finding side lengths, helps us find angles. Remember that every angle in a right triangle comes with its own set of 6 scale factors, those trig ratios. These are fixed and they are specific to that angle. So if we can identify the angle's ratios, then shouldn't we be able to figure out the angle? If every angle has its own little group of ratios, we just have to match. All right, so I'd like you to see, we're going to use 35 degrees. Which of these right triangles has an angle where theta sits that's 35 degrees? Go back and use the slide earlier on where you had all 6 answers for the sine, cosine, tangent, cotangent, secant, cosecant of 35. Can you identify which of these triangles is theta 35 degrees? Go ahead and pause and try that now. All right, well, here we go. I know that the sine of 35 is 0.5736. We've been using that all along. So why not just keep using that? So let's look at all three triangles and see what sine of theta would equal. And remember, sine of theta is that opposite side over the hypotenuse, which I have been color coding as this is 5 green and this is 10 orange, green, orange, green, orange. So let's do that ratio for all three. If I do the first triangle, 5 over 10 is exactly 0.5. That's not 35 degrees. That's something else, which we know from the unit circle is 30 degrees. If I do 8 to 12, that's 2/3. That's not it. Here, if I do 15 to 26, I get 0.5769. Well, given that you know we probably rounded, do you really think all three sides of a right triangle are exact integers? Which triangle do you think is supposed to be 35 degrees? Yeah, bingo, this one. Okay. Yeah, I know it's not exactly the same, but again, given the fact that these were most likely rounded, if you try Pythagorean theorem with 21 and 15, you're probably not going to get exactly 26. This was the triangle that we could best associate as 35 degrees. Now, isn't that super tedious to think about it? So before technology, that's how we had to do it. We'd have to set up ratios, guess and check, compare with our trig tables, and try to figure everything out. But what if, perchance, what if I wanted the value of theta for that second triangle? I know it's ratio. I could go to the trig table, find that, try to find the angle. But don't you think, after having talked about inverse functions, that there's a way to undo this sign, kind of unwrap theta, so that we can get the exact answer for theta if we know that ratio? Like an inverse or something? Lucky for us, we did do that. And if you reviewed your inverse functions, you know exactly what to do. We need to use the inverse sign. So over to my handy dandy calculator, I put in the inverse sign of 15 over 26, and it popped out 35.2, but rounded to the nearest degree, that's 35 degrees. So you can see that's why we chose that triangle. That matchup of 15 to 26 does produce pretty close to a 35-degree angle. All right, let's look at another example. Here's a triangle, and I'm curious to know what theta is. So what I have to decide is, given these two, which ratio I would look up. Well, now we got to start thinking about our SOHCAHTOA. Opposite, adjacent, hypotenuse. I'm matching my adjacent and my hypotenuse. There are two ratios that do that, cosine and secant. Since cosine is a button on our calculator, that's the one we're going to use. Cosine is the adjacent compared to the hypotenuse. So I set up my ratio. Handy dandy calculator time. I'm going to inverse cosine that ratio and round to the nearest whole degree. All right, you try it. See if you can find the value of theta rounded to the nearest whole degree. Go ahead and pause the video now and try it. Welcome back. It was the tangent ratio you were using this time. So we did an inverse tangent and got something around 36 degrees. At this point, if you're still confused about anything, it would be a really good idea to go back and rewatch the parts of the videos that you need to rewatch. Take the time to process it through and think about it. If you're feeling pretty good, then now is your chance to put it to the test. Here are 7 problems that I would like you to solve. You're finding a missing side or angle. You're going to round sides to the nearest tenth and angles to the nearest whole. And then at the bottom, I've given you a word problem so you get a little bit of an application. Make sure when you answer that you include units on the final answer. Some of these get a little trickier than what you might have seen in class. So make sure to just use your smarts to get what you need to figure it out. Go ahead and pause or even stop the video now. Work out all 7, and when you're ready, come back and I'll have the answers for you. Welcome back. Here are all of the answers. If there's anything you're struggling with, anything that you don't understand why it turned out the way it did, and you're not sure what to do, take a picture of your work and send it to me. And that way I can take a look and see what's going on. Good luck, and I hope that you're feeling better about right triangle trigonometry.